Thank you, Madam Governor, for this introduction. Let me all welcome you to our first research session on what I believe is a cornerstone of the central banking and a cornerstone of our understanding of how transmission channel monetary policy works. The session is on price setting, and we have three distinguished speakers with three excellent presentations. We have 90 minutes, so each speaker will have 25 minutes, and we'll leave 5 minutes after each presentation for discussion. So if you may, please refrain from your questions till the end of the presentation. Our first presenter is Oleksiy Kryvtsov. Oleksiy Kryvtsov graduated from University of Minnesota, and for the last 12 years, he has been working at Bank of Canada. He's currently Director of Research at the bank. He's also an advisor at the board for the Canadian Journal of Economics. And today, he will present a paper on price selection, inflation dynamics, and sticky price models. Oleksiy, the floor is yours.
Thank you very much, Jacek. Very happy to be here. Thanks for inviting me, and thanks for having this paper up on the program. You know, I was thinking yesterday, so they say that there's two toughest speaking slots at a conference like this. The one is the opening one, and the other one is right after lunch. So I'm opening, and I was curious, you know, who is the other lucky speaker to speak after lunch. I checked the program, and it turns out to be Mr. Morris Oswald giving the keynote speech. So I guess that leaves me as the only one really under pressure here. I want to first say that I'm really happy that actually the conference is starting with this session, the session that is focusing on how microeconomic data, rich microprice data, can be used for macroeconomic analysis, in particular the analysis of inflation fluctuations, the topic that is very dear to the heart of central bankers, because it symbolizes the way macroeconomic analysis has evolved over the recent past. Central bankers are more keen on using rich information from micro data sets, from big data, as the governor has mentioned. So, and even though there's a lot of information out there, and more often than not, it's not always clear what information can be useful, but sometimes, and more often, there's some useful insights that we draw from the data. So I hope you see it from this session, the first session of the conference. So the topic, the paper is price selection. I have to say that the views I present here are mine only, and they do not represent the views of the Governing Council of the Bank of Canada. My co-author, Carlos Carvalho, is actually at the conference here. He's speaking in the next session, and this is research in progress, so we'll welcome any questions that you have after this. So the theme of this paper is very close to the main topic that central bankers are concerned with, which is keeping inflation low, predictable, and stable. Central bankers are aware that stabilizing inflation more often implies potentially a cost of destabilizing output and employment fluctuations. This relationship, this trade-off, is often referred to as the Phillips curve relationship. If you look at macro data, time series evidence, then you would conclude that inflation fluctuations are actually relatively sluggish. Inflation tends to be relatively stable when there are disturbances hitting the economy. So you would say that Phillips curve has a flat slope, it's flat. It is not surprising, perhaps, because in the micro data, when you observe all these universe of prices over the economy, not all prices adjust. Prices tend to stay fixed at certain levels for a period of a few months. On average, you would say about once a year, a given price would change. If you write a model that simulates the decision of adjusting price infrequently by a retailer, for example, to match this micro data, that model will actually fail to match the macro fact, the flat Phillips curve fact. So that puzzle, that disconnect between evidence that you'd see from micro data and macroeconomic conclusions generated a large literature that tried to kind of solve the puzzle. So theories had to add new features in the models used by central bankers and macroeconomists. So those features, without going into much detail, were based on sort of looking more carefully at imperfections existing in the goods market or imperfections existing in input factor markets. And another strand of literature very popular here is also we're explaining that perhaps sometimes retailers, the decision makers who decide sort of how frequently to adjust prices and by how much, they do not get all the information that is needed to make complete price adjustments, the ones that are justified by economic disturbances to the economy. The third direction, relatively less explored, is the one that we attack today in this paper. And it has to do with the mechanisms, the assumptions about which prices retailers tend to adjust and which they tend to decide not to adjust at any point of time. So we call this very simply price selection. And on the program, you see the title kind of long. There's 3 concepts in the title, but we changed it to just price selection because we think this is really what the paper is about. So let me converge and more narrowly focus on what price selection is. Price selection really is the idea that the selection exists when prices that change at any given point of time are not representative of the population of prices in the economy. Okay? For example, think of a nominal expansion that is expected in the economy that pushes all prices upwards. If at that time, those prices that do adjust by retailers tend to be lower than an average representative price, that feature would mean that price changes tend to be larger than otherwise, and hence the inflation response is more sensitive to this underlying disturbance. Let me explain it in more detail by giving you 2 examples from 2 very popular, very sort of widely used models of inflation fluctuations used in the literature, but those 2 models provide you a different extreme view on the price selection mechanism here. The first one will imply 0 price selection, and the second one will apply some substantial amount of selection of prices. So the first model is the example of so-called time-dependent price adjustment, and it's a very widely used model due to Calvo 1983. It's the backbone of most dynamic stochastic general equilibrium models used by central bankers to make forecasts about the economy. So think of a very simple world where all retailers are the same and they price sort of one generic good, okay? And prices are changed not frequently, but from time to time because they have to pay cost every time they choose to adjust the price. Ideally, if they didn't face any cost of adjusting prices, they would set to the desired price level P star here. But since they have to pay the cost, sometimes they do not adjust their price, and with time those prices would tend to be farther and farther away from desired price P star. So the distance here between a given price at the point of time and the P star represents potential value to this retailer of adjusting that price to the desired level of P star. So the farther away a price on this domain from low to high from the P star, the bigger is the benefit from adjusting the price for the retailer. Now, the assumption made in the Calvo model is that the probability of adjusting any given price here is irrelevant. It does not depend on how valuable it is, would this be to adjust a price for this retailer. So that probability denoted by this flat line at the level of lambda denotes the probability of a price at any level here to be adjusted. As you can see, that probability does not depend on the value of adjusting that price. So the very stock assumption that applies the following. If there is this nominal shock that pushes up P star, pushes up the price level to which I retailer would ideally want to adjust my price to, say up by 1%, what would happen to the probability for any given price that I have in my store to be adjusted? One, given the initial assumption in the Calvo that probability is always constant, no matter what, nothing changes. Even after aggregate shock that I know pushes up the price level at which I want to keep prices in my store, any price in my store has the same probability of being changed. So this is the example where there is 0 price selection. Any price in my store has the same probability of being adjusted. So it's representative of population, 0 price selection. Let me show you the example of another model, which is different. It's an example of state-dependent adjustment. So this is adjustment that depends on the state of a given price. You can think of state as how far this price is from the desired level, P star. So here, the probability of adjustment is very different from the flat one from the previous model. It says that probability, the thick blue line, is 0 or close to 0 when this price is close to the desired price. Why? Because, well, I have to weight the benefits of adjusting this price from its current level to P star. I have to compare it to the cost that I have to pay to change that price. And if my price is close to the P star, it's not worth it for me to adjust it. So the probability of adjusting that price is going to be low. And it's going to be increasing the farther this price is from the desired price. And eventually, if it's far away, the adjustment probability is 1. I'm a retailer going to adjust that price for sure. So you see that at the extremes there, the probability of a price change is 1. Okay? So this relationship of probability of adjustment, the price is very different from the flat one in the Calvo model. So let's see what happens after the same type of shock. So the shock that pushes my desired prices up by about 1%. So the P star is changed by 1%, and the whole probability curve shifts, since it's built around the P star, it shifts to the right as well. So that means that for prices to the left from the P star, for low prices, the probability of adjustment would go up after the shock, denoted by the up arrows on the left-hand side. And similarly, for prices that were high relative to the P star, the probability of adjustment after the shock is going to be lower, because now, after the shock that pushes desired price to the right, and my price was already high, I'm actually end up being closer to the desired price. So I don't have to adjust as frequently. I'm already there just because of the aggregate shock. So this means that both of these changes in probabilities, notice, push the average price more towards the direction of the original shock. Why? Well, it's because the low prices, the prices on the left from the P star, if they get to adjust, they adjust up. They adjust towards the P star. So now that there's high probability of those prices to adjust, the effect on the aggregate price is going to be to push the aggregate price even more to the right, towards higher price. For prices that are on the right from the P star, if they do get to adjust, again, they would adjust to the P star, which is lower than the prices on the right from it, right? So now there's lower probability of high prices to adjust, which again works towards pushing the average price towards higher level. So this price selection mechanism makes the aggregate price level to adjust more flexibly, more sensitively to the original shock. So that's the main application of the price selection, and this is how price selection works. So what we do in this paper, we make it very clear what we mean by price selection, and we propose a very simple measure of how to identify it in the data. So that's the whole paper. And that's what we ask. We ask, well, can we see the price selection in the data, and can we gauge the importance of price selection mechanism for moving inflation up and down? And we're going to propose, as I said, propose a simple measure to do it. We're going to go to the actual microdata, and then we're going to find something. The preview of what we find, the last bullet there, is that we end up finding that the average price level of those prices that adjust relative to population does not move around much with inflation. So that's just to say that prices that adjust, they're more or less representative of the average price. Potentially pointing us more towards the Calvo model, the first of the two models that I showed you. But we're still kind of figuring out exactly the importance of it. But some of the main empirical findings I'm going to show you. So yeah, this is going to be the only equation in the model. Here's how we work with the price selection with actual data. Suppose you have a microdata. I'll show you on the next slide exactly the data we work with. It's just a bunch of prices across a number of goods. I'll be more concrete in the next slide. How do you define inflation? Let's little PIT, define the log price for individual good denoted here by index I at a period T, okay? Take the log difference for each of these goods at the point of time, and take the weighted mean across all goods in period T. That's your inflation. It's just the weighted mean of log price changes. So that's the one you see in the red square. It's a very standard way to define inflation if you have the microdata. We identically rewrite this definition of inflation in the following way. We do 3 changes here to arrive at identical definition. First, since we want to focus on price changes, so many prices do not change, and some do. We want to kind of focus on those that do. We take the number of price changes in front of the sort of bigger bracket. So if you see in the red square there, in the denominator, I denotes the indicator of individual price change. So it's 1 if price change relative to last period and 0 otherwise. So if you take the weighted mean of indicator I across all goods in period t, that gives you the fraction of observations corresponding to a price change. So the fraction of all observations that correspond to a price change. So then the term in bracket is the average size of price change in the data. So inflation basically can be represented as the product of two things. The fraction of price changes, you can think of it as extensive margin of inflation, and the average size of those changes. So you can think of it as intensive margin. Okay? The second thing we do is that before, in the very first identity, we had in the denominator the log price difference for any good. What we do now is we split that difference up and make the average size of price changes, determined in brackets, as the difference of two fractions. The first one is basically the average level of the price changes where they end up, right? So there's a price change, you start from some price level, you end up at some new price level. So the first fraction there is the average new price level of adjusting prices, minus the second bracket is the starting level of those prices that adjust, okay? And the third thing that we did here is, instead of focusing on sort of just log price level for each of these two fractions, we normalize them by the average price index for a given good category. Since we subtract that average, denoted here by cap PIT, there's a lot of heterogeneity across goods here, right? So we define average for each good category, and we subtract it from all these individual price levels. The reason why we do that, it doesn't change anything since we subtract it from each of the two terms, so it cancels out. But the reason we do that is we want to keep both of these fractions easy to work with and have more sort of stationarity properties that make it easy to characterize their fluctuations over time. If it's just price levels, they can be very volatile, especially over relatively short samples that we have. Okay? So what we end up with here is inflation is the product of fraction of price changes and the average size of them. And average size is the difference between the what we call reset price level, the average price level of new prices, minus reset price level, the starting level of adjusting prices. If you go back and you remember how I define price selection, it's really where's the average level of those prices that change relative to some kind of average. And that's the last one, that's the preset price level. So then it makes it very clear what we understand with price selection. It's really sort of, it's summarized by movements in the preset price level. And the main hypothesis that we're testing here is that how much the fluctuations in the preset price level contribute to fluctuations in the average size of price changes to DPT. Okay? And that's what we're going to test in the data. How much do they have? 10? Okay. So here's the data that we work with. This is the micro data posted by the Office for National Statistics in the UK. This is a very rich data set. And it's, for what we know, is the only microprice data available of this class of data available publicly. All others are subject to kind of access restrictions. It's very rich. It covers about 60% of a consumption basket faced by British consumers. This time span is between 96 and 2014, about 117 months of observations across many goods. And that data set provides a lot of other information that is useful for understanding price behavior of retailers, such as how often they use discounts, how often they update the models of a particular good, and so on. There are quite a bit of challenges of working with the inflation decomposition like I presented to you on the previous slide. When you apply it to the data that is so rich, and there's a lot of sort of heterogeneity across different goods, across time, and so on. So things to mention here is that there's a lot rich heterogeneity in terms of price level, obviously, in terms of price changes. There are all sorts of trends going on with the data. You see other behavior. I already mentioned price discounts. There's quite a bit of seasonality, especially for sale prices. Sometimes sale taxes change, so they affect how the level of prices. There are some missing observations and all other crazy stuff that you would see with the microprice data that you have to deal with, and we try to do that too. So let me start getting into the results. So the benchmark specification with which we work is take out sale prices, so ignore price discounts for now, so we call it just work with regular prices, and control for seasonality, so take out seasonality effects. And then apply the decomposition like I explained to you earlier. Here's, and we consider a few other cases, sort of bringing in or out some of the things that we exclude or include, such as sales, seasonality, recession time period and so on. But our main findings are really robust to all these perturbations of the data. The first thing that you find is that if you remember, inflation is the product of the fraction of size, price changes, and the average size. It looks like the average size is the one that is most important for fluctuations in inflation. So you could summarize it as saying that intensive margin of price adjustment is most important for understanding inflation fluctuations. Okay? What we want to do, we want to go inside the average size of price changes and look at the preset price level and how much of fluctuations in the preset price level explain the fluctuations in the DP, in the average size. So we want to focus on which portion of DP is due to preset price level. So let me show you some graphs. So this is the time series for the average size of price changes over months in this data. You see it's pretty jaggedy, but this is the characteristic of inflation time series if you plot it at this frequency, at monthly frequency. So now we want to look at preset price level relative to this time series. It's red. Again, we're kind of testing for whether there is zero correlation between the two or not. And it's hard to see here because there's just too many monthly observations for these time series. But correlation here is pretty low. It's minus 0.15. Let me show you a little bit smoother versions of these time series. So I take out very low and very high frequencies by the Buxton-King filter, and this is what you get. So the correlation here is pretty much zero. Okay, so this already should give you a feeling that the price selection that we document this way tends to be more on the low side, so kind of pointing towards no price selection in the data. Okay. What about the other price, the reset price, right? So the average size is the difference between the two, reset and preset. So if preset price level is not important, it must be that the reset price level explains most of the variation in the average size of price changes. Is that true? So that's the preset in red, preset price level versus the average size, and you can see that indeed they're much more positively correlated. So I want to run the same graphs, but a little bit differently, maybe helping us see a little bit more. So instead of plotting the time series across time, I'm going to do a scatter plot of months, plotting on the y-axis the preset price level, and on the x-axis the average size of price changes. Again, the zero slope of these monthly observations would be supportive of the no price selection in the data. So that's what's summarized by the sort of regression here. You see that the slope is pretty close to zero at minus 0.14. And the interpretation of the slope coefficient in this regression is the fraction of variance of the average size of price changes accounted for by fluctuations in the preset price level. Only 14% in this benchmark case of fluctuations in the average size of price changes can be accounted for by fluctuations in the preset price level. Again, reinforcing kind of the main finding in this paper. Again, just to do a check, what about the other price, reset, the average level of new prices? What about that one? Well, that's 86% of the fluctuation in the average size is due to the new level of prices. Okay, so that, summarize the same slope coefficient summarized here for other cases, and the bottom line is that preset price level explains only up to 16% or so of the variation in the average size of price changes. Okay, and before sort of second to last slide is we go back and we simulate the data using those two models that I showed you at the beginning. One Calvo model, one is Gauss-Lucas model, and we apply the same statistic to those two models because we want to kind of compare where our estimate from the data is relative to those two. What we find is that in Calvo, it's pretty much close to zero, right here. And in Gauss-Lucas is closer to 0.4, okay? So our point estimate is sort of in between, and we're still working on sort of trying to figure out what it really means for each of these two classes of models, but we think that potentially it's sort of more supportive of the absence of much of price selection going on in the data. And so that's pretty much the paper. So we propose a way to think about the mechanisms of what brings about fluctuations of inflation, high to low, and we go back to very, very kind of fundamental assumptions used in models in central banks, which is they assume which of those prices that adjust, where do they tend to be? Do they tend to kind of represent the average price level, or they tend to be not, low or high? And we find not much support of much selection going on with the data. So that's the bottom line. Thank you very much again, and I'm looking forward to this excellent conference.
Thank you, Oleksiy. I think we have a few minutes for some questions. So if there are any questions, please.
Hi, very interesting paper. Well, I was wondering, distinguish two things: the event of changing prices and the amount the price changes. So I understand, for example, the time-dependent model, Calvo, what is unconditional, what is IID, is the probability, the hazard rate of changing the price. But the theory comes with an additional equation with a statement about by how much that new price will change. And that is tied down with the overall price level, expected inflation. I don't quite see that margin, how to do it model-free, really. But I know some people distinguish between extensive and intensive margins of adjustment. The extensive margin is pretty clear, but the intensive margin, I will not understand how it could be that it's completely orthogonal, for example, to preset prices.
Yeah, so excellent question, and definitely once you start building on top of this very simple view of what kind of things make inflation move, up more than others, we start with a very simple one of those elements. And the difference between that element and many others, like the one you're mentioning, is that we actually have direct information from the data about identities of prices that do adjust and do not adjust. So we might as well go and document that part of the overall mechanism. Mind you, after that, we have to go back and think of all other things that could also change this conclusion. And one of the things that we will do, probably using theory, because it's hard to observe sort of where's the right level of the average change of price once they do change, which you're alluding to. So we have to work with theory. So we'll go back to these models for which the first results I showed you, and we'll add some of the reasons for them to adjust more or less, like for example information frictions or whatnot, and see how much, when we apply it to both models, see how much the rankings of this statistic change across different models once we apply these additional features.
Is it working? Have you tried it with the scanner data in the US? I wonder if it would work the same.
We are, as we speak. My array is probably cranking the data right now. I cannot tell you, it's too early for me to tell what comes out of it, but hopefully something that's consistent with the other sources of data. We also have access to Canadian CPI data. Unlike the UK data that I showed you, it's not online. We have restricted access to it, like most people for most of these data sets, and we're working on that one as well.
I adjust for market structure, and because there are oligopolies or more competitive markets, is there a variation in retail prices across different products? And can you model this?
There's no direct information contained in a data set about, say, market concentration. It doesn't come with these data sets. However, if we have this from some other data sets, we can merge it with the price data and look at across section, across different products. We have done it for other papers, so it is possible to have some kind of merge and look at evidence across sectors. Again, I think the advantage of this approach is that you observe. We have direct way of measuring price selection here, so and we do observe differences across products. So what we can do is we can compare. We can exploit the differences across sectors. For example, maybe difference in the market concentration, and see how that correlates with the statistic that I'm proposing across section. So we plan to do that. Was there a question?
Thank you very much. I was wondering, how does this price selection actually change the monetary policy? How should monetary policymakers think differently about the policy given this? And the second question is, it's very interesting. Is there any evidence about the asymmetry of this probability curve you have?
there's a lot of work on trying to estimate these kind of curves, yeah, there are some people think about asymmetry there. Yeah, I could point you to some papers. As I tried to convince you, what we talk about, we think it's central to what should matter for central bankers. And a few examples here is the idea of where the trade-off is between, if we stabilize inflation more than after, same shocks, how much stabilization of output or employment we would give up. It's central for central bankers because it informs the desired level of stabilization. If you think about if you're inflation targeting central banks, you have to be aware of this trade-off because it just tells you if you observe some kind of disturbance going on that will move inflation in a certain way, and you would have to consider adjusting monetary policy. By how much you would adjust monetary policy will be informed by how much you know about inflation response to these fluctuations, and we think this hopefully gives a little bit more information about that.
Thank you for all the questions. Our second presenter is Oleksandr Talavera, who will present a paper, Price Setting in Online Markets, does IT click. Oleksandr graduated from European University in Viadrina, Frankfurt, and before accepting a position of a reader in finance at University of Sheffield, he held positions in DIW Berlin, Aberdeen Business School, University of East Anglia, and Durham University. The floor is yours.
All right. Good morning, ladies and gentlemen. And first of all, I obviously would like to thank organizers, for organizing this conference, a great event, first in Ukraine. But I'm also particularly pleased to thank them for placing my presentation after Oleksiy, because he's already introduced all theories that I was supposed to do in my talk. So my paper, well, maybe Rob will be disappointed, has minimum of Greek letters, like very simple descriptive, but I hope I can convince you that it's still interesting. And well, there is always confusion with words IT, and our session chair did it correctly way. We talk about information technology, not inflation targeting, like in this case. Okay, to start with, still I have to mention, like some papers. When we talk about prices, whether prices are fixed or prices are flexible, there is literature, and I'm pleased, to cite Oleksiy's paper. There is substantial price rigidity, in regular, let's call them brick and mortar stores. And the question, what are the explanations for these rigidities? Let's say common sense, like we are consumers in supermarket, what do we see? Do prices change very often? Well, Ukrainians say maybe they do change. But typically, when we talk about the series, there are explanations. There is substantial price stability for some periods of time. And explanation for this, well, obviously, menu costs, when costs of nominal price, there are costs of nominal price adjustments, search costs. For instance, I don't think many representatives of Polish National Bank know about prices in Kiev and vice versa. Also, let's say when companies monitor, it's costly monitor each other prices, informational frictions, there is uncertainty about demand, economy, and there are segmented consumer markets. And well, researchers and like our first speaker, Oleksiy, told, try to develop a number of models, explanations, and Oleksiy mentioned about Calvo models. There are models of mechanical rigidity. The researchers try to understand where is this, rigidity is coming from, or why, what's happening. And well, actually, I would think researchers take kind of two approaches. Some go into like more sophisticated, let's say, theoretical model calibration, changing parameters. But others, like myself, we take a look on particular, environment and check if, for instance, there are, well, some markets do not have particular, let's say, frictions or obstacles. Maybe we can, explain our theories in better way. And what do we do? Well, we've take a look on online markets. What makes online markets special? Well, first of all, how does it cost to change, price tag for, let's say, Amazon? Well, just nothing. If you have a, let's say, good algorithm, there will be always reaction to other prices. While for supermarket, somebody has to reprint. Second, let's say, lower search cost. Even now, some of us use, phones, tablets, kind of search for information. Well, this wasn't possible, really possible, let's say, maybe 10, 15, 20 years ago. And because of this, we would expect, with lower search costs, we would expect much lower price dispersion. What's about, checking for competition prices, competitors' prices for sellers? If, let's say, 10, 20 years ago, one has to go to place, observe, to retail store and observe competitors' prices. Now it's done, from office. In the evening, just check prices and it's done. And then we would expect, much higher degree of synchronization. Also, online prices give us unique opportunity for price experiment. We can talk about this in the sense of dynamic pricing. What do we mean by dynamic pricing? Do we shop a lot during Christmas? Answer is yes. Everybody is crazy, tries to buy, a lot of, say, presents. I try to avoid kind of high street on this time. But what about our behavior during 1 month? Particular month. When do we get paid? Well, usually we get inflow of money at one particular day, and let's say at the end of month in UK, in Ukraine, I think twice a month. I don't know about US, maybe also twice a month, right. So, and because of this, we've got money, and we go and spend this money. So there should be some cyclicality, and there are increases in demand for a particular good. What's about week? Do we try to find, some consistent behavior over the 1 week, or we go on Friday, on Saturday to do our shopping? Immediately there is question, okay, there are increases in, let's say, demand during week. Do sellers respond to this? Well, maybe yes, maybe no. So we would expect, some experiments with respect to price shocks. And also one might say, oh, well, online, we don't know what we are buying, from which place we are buying. And because of this, let's say some big sellers like Amazon, Google, they introduce, so-called, let's say, trusted seller, phenomena, so that even small sellers could be, let's say, trusted, could be, let's say, consumers could be protected for quality of goods. Okay, so what do? We take a look on online markets, and just to convince you that online markets are in our life, I don't know. For instance, Vlad, can you imagine our life without internet, without Facebook, without other things? I don't think. Even though, if you talk about US-only market, it's retail sales about 5.6%. It looks small, but it increases with tremendous, rate. And let's say average growth of global e-commerce in 2006-2011 was 13%, and it's growing very fast. And if I give you some numbers that, who are the main players on market, we can see the main players already have some metrics that exceed metrics of their offline counterparts. And this paper. So we would like to take a look on, let's say, price setting in online markets. And this unique environment, and we've got, a number of, let's say, features of online market that could help us explain whether, price flexibility could be increased. And one of the beauty of, let's say, this paper is our data. It's just, we've got really unique data that nobody before has ever had. First of all, data are coming from the provider. It's not really, let's say, scrapped, like checked. And that's actually coming from companies that all of you use. And since it's coming directly from provider, it has quite high reliability. Another good feature, and I will show, that there is quite broad coverage. In another papers, some guys, like I and Yuri before, we use only electronics. Some guys use books, CDs. Some guys used, like supermarket goods, but we've got a whole range of goods. Well, it's quite long data. Well, if you talk about online, data, we've got almost, well, typically people collect data for like 3 months, let's say half a year, but we've got relatively long, 2 years. And we've got data for 2 countries, US and UK. And we've got daily frequency, but here there is kind of one small drawback, and it's good and bad, and I will explain later about this drawback. And we observe daily quotes from multiple sellers, and we've got unique price code level data. However, let's say we don't observe really, manufacturing product number for each good. It's still, like clicker, let's say black, that will be kind of a little bit of aggregation up to, let's say, narrow, very narrow category. And now plus and minus. So we are the first, let's say, paper of this. Well, we've got the data of this range that has that quantitative margin. We've got number of clicks. Well, for this wide, number of categories, number of, let's say, weeks that we've got. So far, I think only one paper by and Morgan that had some quantity margin, but it was only for, let's say, dictionaries and over a short period of time. We've got more. However, immediately about drawback, so we observe only those observations that were clicked through. So if some goods at some days were not clicked through, we don't observe, we have to make some imputation, okay? Okay. I don't know about timing because, let's say, I am ready to talk and talk and talk, about it. But just to give you overview, well, what is the destination of, what are the main results that we received? Well, I can talk. Okay. Let's say, given particular features of online market, let's say, no menu cost, lower information frictions, we would expect them to be much more efficient, like higher frequency of price changes, lower size of price changes, higher synchronization, all these things. Do we see this in our data? Answer is, well, maybe yes and no. Yes, prices indeed online are more flexible if you compare with metrics from offline markets. However, the difference itself is mostly quantitative, not qualitative. And what we also found that the models of menu search costs are likely to be incomplete, despite efficiencies that we would assume to happen in online market. We still see that, let's say, sizes of price changes are similar to those in offline markets. Synchronization among sellers or synchronization among goods within one seller is also low. Price comparison, that's also quite interesting phenomena, let's say, is similar to offline. You would expect price comparison to be, let's say, to be almost zero, but it still stays. Okay, price setting, we did some, let's say, correlations, let's put in this way, correlation analysis, and we found that price setting is related to market factors, but not really macro level models. Macro factors only control for, let's say, number of sellers, concentration on markets. But macro factors seem to be not very important, like shocks, like in inflation, interest rate. Also, our data on clicks, it's quite important. It helps us to improve some measures, but it doesn't change overall quality of conclusions. And quite interesting that results for US and UK, despite these countries are kind of different, still remain the same. Okay. And finally, one of the last results that we don't really find any evidence for dynamic pricing on high frequencies. So we don't see any changes that could happen weekly, let's say monthly, or only on very low frequencies, like for US, it's Christmas and Thanksgiving Day, we observe it. Okay, in terms of literature, let's say Oleksiy have already introduced, like price stickiness papers, and one of his, like papers. So our paper is linked to price dispersion literature and price stickiness literature. So that's, let's say. Okay, coming to the source of our data. Our data are coming from price comparison website. If you ever shop online, that's the way how price comparison look like. So we've got, let's say, sellers, we've got their reputation, and we've got quotes. So in our data, we use net quotes, net of transaction costs like taxes, delivery. So for instance, for this good, we've got 1, 2, 3, 4, 5, 6, 7, 8 sellers. And we observe this data daily. And let's say we observe prices and clicks for good seller, and the scale of our data is about 27,000 sellers in US, 9,000 sellers in UK. And we've got about 50,000 goods in each country. So what is a typical good that is sold on this platform? Well, if you take a look on distribution, so we can see that median is about $25, which doesn't seem to be, let's say, quite high. However, when we make click-adjusted, prices, weight by number of clicks, number of, median number increases like 3 times. So maybe clicks matter. So we don't buy cheapest things online. We go and buy, much more expensive things. Okay? And here is composition. Big problem in this type of research that, let's say, Oleksiy uses his sample. I am using my sample, and like comparing results, comparing online, offline results, and or results across papers is due to quite often difficult because of composition of goods is problematic to have the same, and composition of sellers, because our sellers are completely different from sellers in Oleksiy's paper. But let's say, what about goods that are sold online? Obviously, like the largest category is media, the second largest is electronics. Indeed, these are goods that are sold online. But we've also got, let's say, apparel, furniture, software, even, let's say, some services, well, with quite low frequency. About next thing that I want to show, another interesting fact, is related to, let's say, prices. If you take a look on distribution of prices for, let's say, some smartphone in May 2011, number of sellers selling cheapest one, second cheapest, and third and fourth category, and distribution of prices look like this. However, when we make it click-weighted, so we would observe huge increase in the cheapest category. What does it mean? Yeah, well, consumers do not buy expensive, so like there is kind of some degree of efficiency. Okay, that's kind of shortly introducing, like the paper, the main results. And let's start going into paper as long as we have time. Okay. 7 minutes, fantastic. So, what we done? Well, I promise no Greek letters, but there is one, sigma. And what we do, we just try to use our, let's say, number of clicks to have unweighted statistics, or let's say within good weighted, if you have one good number of sellers to weight within good, and between good, so like we just make extra weighting, so like goods with more clicks get more weight. And what do we do here? Well, we take a look, first of all, let's say first phenomenon related to sales. What is sale? Sale is temporary change of prices. How do we account? Do we have to take this phenomena into account? Answer is yes, because it's not proper price change. It just there are seasonal sales. However, it's so difficult to measure sales based on data. Some lucky guys have sales flag. However, when we talk about our data, when we have just sales quotes, we cannot measure. What we can do, and similar to what Oleksiy does, we use a V-shaped filter. So if there is price level, then goes down and then comes back, we define it as sale, and we check what would be frequency of sales in our data. So we check no weight within, good weight between, so like almost like 2%. However, when we check to compare it to offline, the number of sales is almost the same, like 2%. When we take a look on medium size of sale, we observe, like offline sales about like 30%, while we talk about online sales, and if you use our between weights, it's just 4.4. Immediately answer. Frequency of sales online and offline are the same, but size of sales, if you're looking for sale online, it's maybe not a good idea. Okay, synchronization sales. Okay, let me then go to price flexibility, because Oleksiy has started. Are prices online flexible or not? Well, we can check, our median frequency of price changes in our data is about 14%, and it corresponds to 6.6%. Is it a lot? Well, we can always compare it with offline, and we can see like numbers here are substantially higher. So yes, that's true. Online prices change more frequently. What's about absolute price changes? Well, we've got metrics that correspond about 11-10% for online, but what about offline? The same 10%. So let's say when we talk about size of price changes, online and offline markets are not that much different. And we do it for posted prices, for regular prices where we take into account sales. And no matter what we do, statistics, let's say, for price changes are approximately the same. Okay, and maybe I go to the most interesting fact, related, as I say, to dynamic pricing. I've got a lot of things interesting. It's possible to find it online. Okay. So, dynamic pricing is how do sellers react to, let's say, anticipated shocks? And we can talk about idea of Warren and Barsky that firms permanently reset prices during high demand season. And what do we mean by high demand season? Let's say first of all, it's just our Christmas and let's say Thanksgiving, let's say demand shock. And okay. What we find, our result says that, well, there is confirmation for dynamic panel pricing, for Warner-Barsky at a lower frequency. So around sales seasons, Thanksgiving and Christmas, clicks goes substantially up while prices drop permanently down. However, when we turn into higher frequency, like day of week, months, even though we observe that consumers shop more at the beginning of each week or month, there is no evidence that firms adjust the prices more often. And let me show you some figures, here. So we've got, let's say, prices and clicks, and we just, draw no weight, prices. So, well, just kind of, like straight line, no substantial deviation. However, when we adjust it for number of clicks, so we can see, like, after seasons, the prices are likely to be lower. And when we talk about number of clicks, yes, it's true. Americans just shop a lot between, like these weeks between Thanksgiving and Christmas. And now let's turn to within week, let's say, differences. Here are day of week click share in percent. So what do we see? Surprisingly by not, but online shoppers, spend more clicks on Mondays compared to, let's say, Friday and Saturday. Is it true, Americans? Well, so we still observe, from 12 to 16%, we talk about 25 increase in number of clicks. However, what about, let's say, price changes? Let's say if you take a look on mean price, yes, there are some difference. But when we take a look on weighted mean price, we observe almost no difference. Okay, and the same for the same idea holds for within month deviations. Okay, then in conclusion, I would like to say that yes, online prices are a great opportunity. It's, let's say, more efficient, way how companies can make business. But despite all these things, there are frictions that still remain. And current models, current macroeconomic models may need to include extra elements to account for facts that we observe in our data. Okay? If there are questions.
We have a few minutes for questions, if there are any in the audience.
Sasha, thanks for this research. Following what was said by the governor in the introduction speech in respect of new technologies and following your research, which I know you are already ongoing for quite a time, what is the future of the statisticians in different national officers, in national offices in globally? Because actually, with access of big data, with access of open data about the online sales and the online's growing, I think one day we will just not need all these people who are calculating the statistics on the monthly base, and we can do it by time, on Friday evening, just looking on the prices.
Yes, thank you very much, Vlad, for this question. Well, for another project, I spent like 5 years just to collect data, and it took, another 3 years to write paper. And during this process, I've learned a lot of interesting and fascinated, things. Using online data, let's say banks like National Bank can't, have hand-on inflation, that they can get information almost instantly. We are talking about weekly inflation. That's exactly what we started doing together with Sergei at the National Bank of Ukraine. And another thing, related to, let's say, big data and big price level data. That's what we're doing related to synchronization of prices among sellers, price flexibility things, price duration, and among different categories, and also effect of internet of our life and how this affects really, price changing behavior. I gave you American, some data for American sector. We are talking about 5.6% of the total retail, but this number is growing and growing very fast. And yes, there is definitely need for some type of data analytics that can get, ready to use online data. Yeah.
Do we have any other question?
Given how similar your results were for the online and offline, and let me see how we can formulate it. So there's this big friction that you were talking about earlier, that offline retailers, it was harder to check the competitors' prices because they have to go to the store physical and have a look, go to the supermarket and go have a look. Now almost virtually all retailers have their website and they record their prices there. And the prices are virtually the same, online and offline. So if I'm shopping for whatever, new fridge, I'm gonna check online, I'm gonna check the different retailers, I'm gonna physically walk to the store to have a look at it, and the price is gonna be the same. So can your similarities between the online and offline be driven by that? That it's just easier to see the competitors' prices and it's not that hard to change the sticker on the price. So the actual menu cost is not that hard, it's not that costly anymore either. It just takes a second to change the sticker.
All right, thank you very much for question, Julia. And let's say, first of all, like there is assumption that online prices are always cheaper, and that put a lot of pressure to offline sellers to go online. If you talk about big Americans, sellers for electronics, they are all present online, but they were not online 15 years ago, right? Well, maybe some, and yes, we see kind of consequences of this switching online and change in efficiency. Yes, there is still need for, as you say, showrooming. I think that's the right English word, but if you talk about online, and another paper of mine, so we take a look on small sellers that are present only online. And that's where we got, a lot of efficiency. When we talk about bigger sellers, then there are some frictions. There are other factors that matter, and prices remain slightly more, stable. Right.
Okay, thank you. Let's move to our last presentation. The last presenter is Anton Nakov. Anton graduated from Universitat Pompeu Fabra in Barcelona. He's currently a senior economist at European Central Bank, but he held also a position in Banca de España, IMF, and Board of Governors. And today he will present a paper, State-Dependent Pricing and the Paradox of Flexibility.
Yeah, all right. Thank you very much. Thanks a lot for having me on the program. It's a great pleasure to be here. So this is joint work with Luca De Dola from the European Central Bank. But let me say straight away that none of what I'm going to say is the official opinion of the European Central Bank. And in fact, these are our own opinions and views, and they do not necessarily coincide with those of the ECB. So let me, with this disclaimer, move straight to the question of interest here. So this is another paper on price setting and that looks at the flexibility or stickiness of prices. But the focus here is somewhat different. I'm interested in the question whether increased price flexibility is intrinsically stabilizing. And here we already saw in the first two presentations this difference between models of state-dependent pricing and models of time-dependent pricing. I'm going to talk about this difference as well. And in particular, the leading models nowadays are those of state-dependent pricing, basically because they account for some features of the microevidence on price changes, and that's how the profession has moved to microfounding these models based on microevidence. However, as Oleksiy mentioned, in these models, money is almost neutral, unlike in time-dependent pricing models as Calvo. And but generally, there is this notion that increased price flexibility is stabilizing, at least in the sense that it mutes the real effects of demand shocks. Okay, and so what we do in this paper is we show that this notion is not totally correct. it all depends on the systematic monetary policy. And in particular, we show that if monetary policy leans sufficiently against inflation, then the notion is correct. However, if monetary policy does not lean against inflation and allows for a drift in the price level, then increased price flexibility may lead to higher output volatility in response to demand shocks. Now, why is this at all interesting or relevant for central banks? Well, this is, I would argue, very interesting for central banks because in recent years, policy nominal interest rates in many advanced countries have reached very low levels, levels beyond which central banks are unable or unwilling to go further down. And I would argue in this presentation, this is exactly the situation when increased price flexibility leads to the amplification of shocks and to destabilization of real variables. Okay, we're not the first people to have thought about this, as usual. There is an old literature on this topic, but by now there is a growing recent literature showing that constant interest rates may lead to the amplification of shocks. For example, in papers by Woodford, Cristiano, Eichenbaum, Rebello, Del Negro, and others, show that when nominal interest rates are constant, a drop in the natural real rate has larger deflationary effects than if the policy was leaning against the disinflation. That the government spending multiplier is larger than 1 and potentially could be much larger than 1 when nominal interest rates are constant. And that forward guidance, these are announcements about future changes in monetary policy, is very powerful. So what is the mechanism behind this? How does it work? It all goes through the real interest rate in the Euler equation. So suppose that the nominal interest rate is held constant for periods t from 0 to capital T, and afterwards monetary policy follows some rule, then the nominal interest rate drops out from the Euler equation, and what is left is that consumption today equals a cumulative sum of future inflation plus consumption at period t, when the central bank stops the constant interest rate policy, which, if you assume that t is far enough into the future and then ct is approximately 0, then this is proportional to the difference between the price level upon exit from the constant interest rate policy and the price level today. And now suppose that there is a shock to government spending. It can be another demand shock, but just for example, think of a shock to government spending. What will show that it all depends on the monetary policy rule in place. So if monetary policy is such that on exit the nominal interest rate follows a Taylor rule, okay, of this type, okay, we know that this rule stabilizes inflation but not the price level, and it allows for a drift in the price level, and therefore P capital T will be greater than P0, and there will be crowding in. Consumption today will increase, and given that there is an increase in government expenditure, output will increase by more than the increase in government spending. And so the government spending multiplier will be larger than 1. But if instead monetary policy is not so accommodative, if, for example, money is held constant, okay, then what happens is the price level jumps on impact, but in the long run, the price level converges to its initial level, and so we have the opposite relationship. P capital T is smaller than P0, and we have the usual crowding out. So government expenditure crowds out private expenditure, and the government spending multiplier would be less than 1. Okay. So the title contains the words paradox of flexibility. So what is that paradox? Let me spend a moment on this. So the paradox of flexibility is that increasing price flexibility leads to a larger drift in the price level and therefore a larger amplification of shocks. Why is this a paradox? Well, because in the limit, when prices are fully flexible, that means 100% flexible, they react immediately and fully to the shock, then we know that the government spending multiplier is less than 1, okay, and there is no amplification of shocks. But as we move towards the limit, as you increase price flexibility towards the limit, the multiplier increases. And so there is this non-monotonicity in the relationship. So in particular, increasing price flexibility leads to a deeper recession and deflation when the economy is hit by a deflationary shock, as shown by Eggers and Krugman. And it also leads to a larger government spending multiplier, as shown by Cristiano and co-authors. Now, one thing that all existing papers assume is that price setting is time dependent. In particular, they assume Calvo pricing. And as we already mentioned, the profession has moved beyond Calvo pricing and is studying models of state-dependent pricing, which is what we do in this paper. So we extend this analysis to models of state-dependent pricing, and we look in particular at the effects of a shock to government spending across three pricing models: Calvo, fixed menu cost, and an encompassing model. So this encompassing model is what we call smoothly state-dependent. We call it so because the adjustment probability is a smoothly increasing function of the adjustment gain. So this is very similar to what Oleksiy showed in one of his slides. And we compare monetary policy rules that lean against inflation with ones that keep the nominal interest rate constant. So what do we find? We find that with monetary policy that doesn't lean against inflation, state-dependent pricing produces even larger amplification than the Calvo model. So in that sense, more price flexibility is destabilizing, and the paradox of flexibility is not just an artifact of Calvo pricing. Okay, so after this brief introduction, let me go to the model. I will briefly show the model. I understand here is a general audience, so I will not spend too much time on each of the equations, but nevertheless, we'll show you the basic ones, and then I'll go to the results and conclusions. So the model deviates in two ways from the textbook New Keynesian model. In particular, there are idiosyncratic productivity shocks to firms, and the second deviation is that pricing is state-dependent, and it nests Calvo and fixed menu costs as two extremes. And as I said, we study monetary policy with and without a drift in the price level. So on the household side, the model is completely standard. There is nothing new here. We assume that there is a representative household with this utility function. Consumption is an aggregate of differentiated products, and the household faces this nominal budget constraint. And it chooses consumption, hours worked, bond and money holdings to maximize expected utility, as is usually assumed in the literature, subject to the budget constraint. And here the optimality conditions of the household, which are completely standard. Okay. Now, where the model differs from much of the literature is that firms produce output subject to idiosyncratic productivity shocks. So output is Y, and it's a linear function of labor, of hours worked, but it is hit by these shocks which follow a certain stochastic process called AR1 process. And firms face demands both from the households and from the government, which takes the same CES shape as private consumption. Okay, so the demand curve is standard here. The only difference is now we have private consumption plus government consumption. We can define period profits as revenues minus costs, and we have the usual discount rate. So with this, we can write the value function of a firm that produces with productivity A, price P, and some aggregate state omega, as the sum of period profits and expected continuation value, where this is just the value of the firm tomorrow with the new shocks, and the expected gain from adjustment, which is now the probability of adjustment lambda times d, which is this d is the difference between the maximum value that the firm can attain by varying its price p and the price it currently and the value it currently has at its current price. Okay, so where the innovation is that for this lambda function, we postulate a functional form that allows us to nest the Calvo model as one extreme and the fixed menu cost as the other extreme. So in particular, when this parameter xi goes to 0, this expression collapses to lambda bar, which is just the Calvo model with a constant exogenous probability of adjustment. And when parameter xi goes to infinity, this converges to an indicator function that takes a value of 1, probability 1, whenever the loss from inaction exceeds a certain parameter alpha, which can be thought of as the menu cost, and otherwise it takes a value of 0. So a key parameter in our model, in the smoothly state-dependent pricing model, is this xi. So how do we discipline this parameter? We looked at evidence, micro-evidence on the size distribution of price changes, and here you see in the blue shaded area the histogram of price changes from AC Nielsen data documented by Midrigan. And with the different lines, you see different models, the fixed menu cost model, the Calvo model, and the smoothly state-dependent pricing model. You see that the fixed menu cost model generates these two big spikes around the adjustment thresholds, around the so-called SS bands, and it has nothing in the middle and very little in the tails of the distribution. Okay, so it has a really hard time matching the evidence on price changes. The Calvo model, on the other hand, really overstates the middle of the distribution. In particular, the highest probability of price changes is those tiny changes around 0. And the one that best fits the evidence is a smoothly state-dependent pricing model with parameter xi equals to 0.23, as it turns out. Okay, associated with these different histograms of price changes are so-called hazard functions, or probability of adjustment as a function of the loss from inaction, which you can see here for a high value of psi equals to 50. This approximates a step function, as in the fixed menu cost model. For the Calvo model with a psi very small, it approximates a straight line, okay, at lambda bar, the exogenous probability of adjustment. But for intermediate values such as psi 0.23, it is just some function that starts at the origin and crosses here at this line and then increases towards 1. How much time do I have? Okay. All right, so the rest of the model is also standard. So, well, monetary policy here is assumed to be such that the nominal interest rate is held constant at steady state for capital T periods, after which monetary policy follows a Taylor rule. And government spending is just assumed to follow an AR1 process. Okay, so in order to simulate the model, we need to calibrate it, to put some values, to give values to the parameters. And the way we do it is we take several parameters directly from the study by Golosov and Lucas for comparability. Then we set the inflation target equal to 1. This is the gross inflation target. So it's consistent with 0 inflation, as in the AC Nielsen data set that we study. The inflation reaction coefficient is set to 2, which is a common value in the literature. The length of the constant interest rate period is set to 24 months or 36 months. So the model is a monthly model. And this is as in Jacek and Linde. And then some persistence parameters are taken from previous papers of ours, and this is just the estimate of the state dependence parameter that I showed you how we do by matching the size histogram of price changes. Okay, so just some preliminaries before going to the main result. Now, it can be shown that in this model, the flexible price multiplier, or the government spending multiplier and the flexible prices is always less than 1, is bounded above by 1, okay? It's just equal to this ratio of intertemporal elasticity of substitution and the inverse Frisch elasticity of labor. And this will be our benchmark, okay? So a multiplier of less than 1 will be 1 which is close to the flexible price benchmark, and a multiplier above 1 will be the one that we obtain with constant interest rates. So this is the log linearized consumption Euler equation, okay? It is the so-called Ayas curve, and here is the Phillips curve. Okay, it's a forward-looking expression for inflation that depends on future inflation and future output gaps. And it can be shown analytically, actually, that in this model, when the monetary policy is standard, it follows a Taylor rule, the solution for the multiplier is this expression here, which is always below 1, okay? So it's, in a sense, close to the flexible price counterpart. And if you take derivative with respect to kappa, you will see that more price flexibility or higher kappa leads to a smaller multiplier. Okay, so there is nothing strange in this result. The more flexible prices are under standard monetary policy, the more you converge to a flexible price limit of a multiplier below 1. But now, okay, so that's the first result. Under an active Taylor rule, more price flexibility leads to a smaller multiplier, okay? So it's stabilizing in that sense. Now, when we do this analysis with state-dependent pricing, what we see is that nothing much changes. So here we have a 0.1% shock to government spending, okay, with persistence of 0.8, I think. And, you know, prices start rising in response to this shock. The nominal interest rate, however, increases by more than 1-to-1 with inflation, which means that the real interest rate rises. And because the real interest rate rises, consumption drops. And that happens across the three models. And in fact, if you look here at the fiscal multiplier, it is always below 1. And the more state dependence you have, the more you move from the red line towards the green line, the smaller is the multiplier. Okay, so more flexibility, smaller multiplier. Okay, so that's the first result. Now, as an aside, if actually monetary policy is such that money is held constant, okay, the multiplier is also less than 1. Okay, so you can see this again here, where the three lines here are again represent the three different models, Calvo, smoothly state dependent, and fixed menu cost. And again, as you move towards more state dependence, you move towards a smaller multiplier. Okay, and again, here is an artifact of the movement of the price level. Notice that here prices jump on impact in response to the shock, but in the long run they converge back to the original price level because money is constant. Okay, I will skip these two slides in the interest of time and go straight to the second result, and this is that under monetary policy that allows for a drift in prices, there is much larger amplification under state-dependent pricing. And we can see this here. So now we have the same shock, 0.1% increase in government spending, Now, notice that prices start rising both in the Calvo and the smoothly state-dependent pricing model, but they rise much more sharply in the state-dependent pricing model. Why is that? This is the result of a selection effect that Oleksiy talked about. The fact that the size of price changes and probability of price changes are correlated. In particular, there is an increase in the probability of adjustment of those firms that desire large price changes, and therefore the price level becomes more flexible, even holding fixed or almost fixed the overall fraction of adjusters. So you see that the fraction of adjuster barely moves, but nevertheless, because of the selection effect, the price level is much more flexible. And what this results in is a multiplier of close to 2 in the Calvo model, but close to 8 under state-dependent pricing. Okay, so this is a very, very large multiplier. And we do some robustness checks. We check what happens, in the fixed menu cost model. Actually, in that model, the multiplier really explodes to values of 50. And we check what happens when you increase the time of keeping the nominal interest rate constant, and again, the multipliers become larger. And with that, let me conclude. So we find that with monetary policy that leans against inflation, under state-dependent pricing, the fiscal multiplier is close to flexible prices. There is nothing strange. But with a rule that does not stabilize the price level, that keeps the nominal interest rate constant, there is a much larger amplification under state-dependent pricing. And the largest amplification, in fact, is obtained in the Golosov-Lucas model of fixed menu costs. Thank you very much.
We have time for a couple of questions for Anton.
Yeah, you focused in the presentation on the fiscal multiplier and demand shocks. What can you say about supply shocks and the economy's response?
Right. Yeah, that's a very interesting question. And in fact, I have a slide. Oh, my presentation is gone already. Oh, there it is. So I think I have a slide at the end with a TFP shock. And with a TFP shock, it is always the case that with state-dependent pricing, there is more volatility in output, regardless of whether monetary policy leans against or doesn't lean against inflation. Yeah.
Anton, can you talk a little bit about the monetary policy that imparts a drift to the price level? Because you didn't talk about that, so I was just curious.
Yeah, well, that's the one that keeps the nominal interest rate constant for cap T periods, and only then the Taylor rule kicks in. And because it kicks in so late, it stabilizes the price level at a much higher level. And because of this first mechanism that I showed, because of this difference between P cap T and P0, that generates the crowding in of private spending.
That's a good question. This is an example when this is, I guess, a bad policy prescription, right? Because monetary policy, if you run an exercise and ask what was the best way to respond to this for monetary policy, so if you realize that prices are very flexible, then you probably should kind of let it go, because you know that if you otherwise it's going to cost you in terms of destabilization of output.
Sure, we're not advocating at all any kind of policy. We're just doing a positive analysis here, and the question of whether these governments, you are forcing people to work a lot, so that creates this utility of work effort. And so there is no presumption at all that this is a good policy. But it's just a cautionary note that, for example, in times of austerity, if you are trying to contract a lot government spending and prices are flexible and you cannot move the nominal interest rate, then you can get a bigger contraction than what you thought.